Welcome back. In today's video, we want to talk about the switching action in an electric circuit. So in this case, we see that the switch connects or disconnects our voltage source connected to some circuitry. Could be resistors, capacitors, could be whatever. Here we have a unit step function, and we have some other graph that would describe the switching action. So and as you can see, let's just point that out, that green is closed and red is open. So in logic, we know that a 1 is on for a switch. If you see a logic switch, on and off, we know that 1 is on and a 0 is off. So the unit step function is a step, and it's a step of 1 unit. So it should be 1. Also, it's important to note that, as you can see, we have time, and the unit step function is a function of time. So for t less than 0, you can see that the value of the unit step function is 0. And for t greater than 0, the value of the unit step function is 1. And notice that it is not greater than or equal, so we do not include the transition, because actually the transition, this is a ideal unit step function. In the real world, a unit step function would look somewhat like this. So there would be some transition, and we'll call that delta t. So it takes some time for this to go from 0 to 1. Okay, so normally we write that as a piecewise function. So that would be 1 for t greater than 0, and will be 0 for t less than 0. Now, if we include our circuit, we then can say that voltage would become a function of time based on our switching action. So we'd call this V of t. And the magnitude would be that when the switch is closed, the circuit would see a magnitude of V0, which is the voltage, the value of the voltage source. Okay, so actually this then becomes V of t is equal to V0 U of t. And U of t will describe the action of the switch. So we can then change, or we don't have to change, we just know that where the 1 is, we have V0, and V0 times 0 will be 0, so it doesn't change. So let's talk about the closed. So before the switch is closed, there's no current, there's no voltage being supplied to that circuit. So down here, let's just put our 0 here, put V0, 0 volt, and let's put, say, 2 seconds right there. And 2 seconds will be equal to capital T, because we already have the common T describing the time axis, or time in general. So capital T will be some instance in time. So we can mathematically describe the switching action using our mathematical expression. If our switch is closed, that means the switch has to be open before it's closed. So when the switch is open, there's no voltage being supplied to that circuit. So here we see we have 0 volts. And at 2 seconds, that switch is then closed. So then our circuit starts seeing V0, which is the value of the voltage source. So a switching action of our switch being closed will see a graph as such. So that can mathematically be expressed as, let's just put C for closed, and we can just fully write that out. So V of t is equal to V0, circuit C's V0, and now the action of the switch to describe when that switch was closed is t minus 3. So the difference between these two is that the minus 3, let's just make this minus 0. So as you can see, minus 0, t minus 0, t subtract 0 is still t. So then the step function stays at the initial position. However, when we subtract 3 from that, we see that the step function is delayed 2 seconds, and that should be 2, not 3. It's delayed 2 seconds, and that delay is a representation of our switch being closed. So what about our switch being open? Let's just use OP for open. If our switch is open, that means our switch was already closed. So when that switch was closed, the voltage went to V0. So if that voltage went to V0, so in all time, we have a value of V0. So that circuit is seeing that value of the voltage source. So now, when that switch is closed at 2 seconds, so it was already at V0, then we just get a dip, and it transitioned to 0 volts. So now that switch is now open as indicated in red. Blue is just the transition. So we can represent that by V of t is equal to V0 U of t, and that should be not minus 2, but that should be 2 minus t. So what happened is that not only did our graph shift to 2, we have the time reversal property taking effect. So now we shift our graph 2 to the right, which is we delayed it, and then we turn it around, which we reversed it in time, and then we get the following. So the negative t is in signals and system is kind of like the time reversal property. You multiply the axis by negative and you get a reversal of that. So these two right here describes the, and you know what, I should have written that in red and one in green, but we know this is closed and this is open. So that's basically it for this video. Also, what I was talking about this transition, normally that would look somewhat like this in the real world. So that's non-ideal. And then that would be delta t. So 0 volts, and that would be V0. So this would take some time to transition up to the voltage or the value of the voltage source. So, you know, that's it for this video. See you in the next one. Bye.